So next semester I'm teaching close to your neck of the woods in the Garden building.
Oh yeah?
Yeah.
Is it what kind of class is it?
It's this class on ethics and data science.
Ah.
So my room, they give me is there. So. I taught this last year, but you know.
See if I can sit in on it.
You don't have too many courses already.
I know. He's like, I don't want you taking any more classes.
Yeah.
So
Alright, so I promised that we'll spend the last two lectures, today and Monday, on review. And the point of the review is partly to remind ourselves of all the things we've done in the class, but it's also to get you kind of warmed up for, you know, the exam on Wednesday, and then of course, sort of back into the right frame of mind to think about things. And so, what I also want to do is sort of remind you about the topics, what we covered, and also, you know, some of the things you might need to be reminded of, and how you prove things, how you reason about things. There are all different aspects of reasoning that you use in different places. So I'm going to break it down, I guess, into two parts. We'll do so one part of the class today and one part of the class on Monday, and we'll see how far we get today. Right? So we'll start in chronological order back in the very beginning, and then we'll move our way through the topics till we get to the end. So I think the first thing we covered, of course, in this class was divide and conquer, but even before that, right, we talked about something more basic, this idea of a reference relation. And these are going to be very important because if you have to analyze many standard algorithms, even randomized algorithms, by the way, which I can talk about how to do randomized recurrences, but if you have to analyze many algorithms, a recurrence relation is going to be a way to reason about the behavior, especially if the algorithm is what property of an algorithm would make it almost necessary to use recurrence relations to solve. So I've heard only one word, the rest of it required recursion. Yes, if you're using recursion, then there's no obvious way to analyze the behavior of the algorithm. You can't just say, okay, this step takes so much time. You have a recursive step, which means your running time is expressed in terms of your running time for a hopefully smaller version of your problem. Right? So you end up with recurrence relations anytime you have a recursive algorithm. And we've seen many recursive algorithms in this class. We've seen divide and conquer, time programming, some greedy algorithms as well. And a lot of problems can be phrased in a recursive way, right? Just because it's easier to think recursively. And so, you know, of course, when you do recurrence relations, you're basically saying, what is the running time of this algorithm? So usually, or what is the resource usage, whether it's space or time, right? Sometimes it might be space, and you have some kind of parameter. Let's say for now, if it's time, you just use T of n. This is the time it takes to run some input of size n, the worst case input of size n. And usually it's some function of, you know, T of n minus 1, or T of n over 2, or a bunch of other things, right? And in general, to solve this recurrence relation, you need a bunch of different tricks, right? And so maybe we should just go over some of the tricks. And one of the most basic tricks, so let's say the tricks we have. First one is just what we call unrolling, right? And unrolling, for some kinds of recurrences, this works very well, right? So if you have, say, T of n is equal to, I don't know, let's say 2tn minus 1. Let's just leave it at that. And we have some base case that t of 0 is equal to 1. Okay? So really simple records. You probably might even know the answer already, but again, like I always say, that's not the point. The point is, how do we solve this? Well, if you don't know any better, you might say, okay, well, I can just expand this again. If tn is equal to 2tn minus 1, then tn minus 1 is 2tn minus 2. So we can write this as 2 times 2 of tn minus 2, which is equal to 4tn minus 2. And then you can write it again, and it won't be too hard to see. This will become 8 times t of n minus 3. And so on. So you're unrolling it, right? And the trick of unrolling is you then now to look for a pattern. And in this case, the pattern seems to be that every time you subtract 1, you multiply by 2, right? So this becomes something like 2 to the I t of n minus I. And once you get to that form, then things are good, because now you can say, okay, what's my base case? My base case is t of 0. For t to be, for to get a 0, I need to put I equal to n, and I can put that in there. So if you keep unrolling it, this becomes all the way down to 2 to the n times t of 0, which you said was 1, so this is 2 to the n, and you're done. Right, so unrolling is an easy way to solve the recurrence if the recurrence admits unrolling. Not all recurrences admit that kind of trick. Right, so this is just one of the tricks. For example, if you try to unroll, say, a recurrence that looks a little bit different. So if we try, for example, t of n is equal to, instead of 2tn minus 1, it's t of n minus 1 plus t of n minus 2. And of course, because there are two things, you need two base cases. So we'll say t of 0 is equal to 0, t of 1 is equal to 1. Now you can try unrolling this, and presumably you know what's going to happen. This is the Fibonacci recurrence. It's going to become an unholy mess. You're not going to get anywhere useful with this. And so that's, in fact, a good test for why unrolling may not be the right answer, right way to the whole problem. If you don't wrap this, you'll say, okay, this is basically, this gives us 2t n minus 2 plus t of n minus 3. And this might give us 3t n minus 3 plus 2 t n minus 4. And I can do this for a while. I'm not really seeing a useful pattern, not yet anyway. I mean, you will, if you start looking very carefully, you'll start realizing there's a Fibonacci pattern coefficient. That's another story. But it's not going to be easy to do anything. And this is also a sign that the technique is not working. If you can't unroll it a few steps and start seeing a pattern, then more likely than not you have a problem. Right? So that's one way to tell that unrolling is not working. But of course, it might be that it's working, you just can't tell. Because if you have this recurrence, right? Then this you can unroll as, it'll be n plus n minus 1 plus n minus 2, and it'll go on. Which is fine if you know that this series can be solved and there's a nice closed form expression. But it's very bad if you've never seen this before. I'm pretty sure all of you in this class have seen this kind of expression, but it might be a more complicated version of this maybe, or something else. So sometimes it can be unrolled and there is an answer. You just need to be aware of the fact that there's a sequence that you can actually solve. So at least this is not recurring. That one is a recurrence relation that you can't simplify. This at least is just a regular summation, right? And one thing I'm going to allow you to do for the in-class exam, and I'll post a note on this today, is bring like one sheet of things like, oh, you know, a cheat sheet if you will. So like, oh, the sum of all n plus n minus 1 is n times n minus 1 over 2. You don't have to remember those things. So I'll allow you to bring one sheet of paper with whatever you want to print. In fact, there's a very nice sort of cheat sheet. Of course, it's 7 pages long, so you can't use it. But there's a nice cheat sheet for all these basic things in algorithms and theoretical computer science, which I might share with you just for your own reference. It has all the usual things you need. So the goal again is not to memorize things. So you'll have one sheet of stuff if you want, and there'll be some things you'll need. So unrolling is a very powerful technique, but sometimes it won't work. Sometimes it won't work because you just can't get it to work. Sometimes it won't work because you don't know enough to know that it can work. So you have to sort of watch out. Okay. What other techniques are you familiar with for solving a recurrence solution? Marshall theorem. Okay, let's talk about the Marshall theorem. So this is a very powerful theorem, right? It gives you a very powerful sort of hammer to look at a problem. And what does it look like? Can someone tell me what that looks like? So T of n, it takes any recurrence that looks like okay. So what this is saying is that look, if the recurrence happens to be in a form where you're dividing the input into pieces of a significantly smaller size, they're a small fraction of the input, and there's some number of copies of them. So there are each piece of size n over b, and there are a copies of them. And then you merge doing some f of n work, or you use some time in splitting, so that fn could involve both the amount of work it takes to split them up and the amount of work it takes to merge. And the recurrence is in fact the t of n over b. We know in general how to solve this kind of problem. Notice that none of the two previous examples I showed you, or three examples, can be solved using this method. So this method is not universal, right? For neither 2tn minus 1, nor tn minus 1 plus tn minus 2, nor tn minus 1 plus n does this apply. Because you're not dividing into these small pieces. So you cannot do this. A and b have to be constants. Nevertheless, there are many cases in algorithm design where you will see something like this. And you should know that if you have an algorithm that divides into pieces and combines them, there's a way to solve the recurrence. And again, we didn't derive the proof of this in class, but we know that there are a bunch of cases. And what do the cases look like? So you basically have a bunch of cases. If a f of n over b is less than some so less than c times f of n for c strictly less than 1 for all n greater than 0 asymptotically. If a f n over b is greater than equal to capital C times f of n for capital C greater than 1 for all n greater than 0. The third case is a f n over b is equal to C times is equal to not C, right? Just f of n, right? Yep. Again, for all n greater than 0, and then there's a fourth case when we don't know what to do, right? What happens in the first case? And again, you can memorize this, but it's helpful to know why. If this is happening, remember the first term represents my recursion work. The second term represents my merging work. If this is the case, then the merging is more important than the recursion, and so the merging wins. And so the answer is O of f of n. Second case, the merging is weaker than the recursion. So the recursion wins. Well, what do you do with the recursion wins? You get this somewhat more weird expression, n log of b base c. Did I get that right? No, I got it wrong. What is the correct one? Log of a base b. Because you're splitting into b parts, that's the base of the log. And what happens if they're both equal?
And log of f of n log. Something like this.
Something like that. That is not an acceptable answer. A bunch of randomly chosen answers followed by something like this will not get you any points. Just so you know. Yes, what is the answer here? Anyone who chooses not to guess? No? Whatever the answers was actually correct. Just that we guessed it, so it doesn't count. Everyone log in. And it could be n log a base b log n also, because they're both the same. If this is true, these two are going to be the same. And the extra log factor is just because of the way we equal this. So there are three cases when this works. And again, we've talked about this very briefly though. These three cases don't cover all possibilities. Right? Because these two things have to be true all once n is large enough all the time. And that has to be strictly less. This has to be true all the time. Right? This equality has to be true. You can get cases where none of these things are true, in which case you can't use this. Okay. And this again is very helpful. For any of the standard recurrence we've seen. So for example, when we did Karatsuba, we did T of n is equal to 3t n over 2 plus some constant times n, right? Just by invoking the Master theorem and observing that, you can really eyeball this and say 3n over 2 is much more than n. Let's just say this is n for now to make this. Right? Then, actually it doesn't matter. It doesn't matter. Let's see now. You'll get basically the first case, second case applying, and so the running time t of n is equal to log n to the log of 3 base 2. I don't know if you noticed, by the way, but a few weeks ago, some researchers basically finally, so we looked at this thing for integer multiplication, right? And there's a better way to do this using Fourier transforms, which is much better than this, which is roughly n log n times log n. And some researchers managed to get what we believe not to be the best bound, which I think is like, I don't know what to say. I think it's just n log n. There's no extra log n factor. And that's the type. We believe that's the best bound you can get for a function loop. So this is how they happened 3 weeks ago. That they got the final best answer for this question, even though this has been around since the 60s. This was, by the way, a homework sort of basically the way this algorithm got proved was that I think it was Kolmogorov who was giving a lecture in class and said, oh, this is how we multiply the integers and we can't do any better. And one of the students in the class said, that doesn't sound right. And when it proved, got this algorithm out of it. So back in the 50s. Okay, that's fine. So the Morse theorem is very powerful when it applies. But there are cases where it doesn't, right? Trying to remember some standard, there's some nice cases when it doesn't apply. Trying to remember one. Well, of course, like I said, all the previous cases, even the syntax of the Morse theorem doesn't apply, so you can apply it. In some cases, the syntax applies, but you don't get one of these cases, and so you can apply it there. Okay. So now we have unrolling, we have the Morse theorem. What else do we have? We have one other method that is, I would say, it's always guaranteed to work. In the sense it will always give you some answer, or give you a correct answer. Guessing and checking. So guess and check, right? So the guess and check solution is basically literally just guess and check. So now I have something like t of n is equal to, I don't know, square root n t of square root n plus n. You can't by the Morse theorem, and you could unroll this, but it gets a little messy. The way to do a guess and check is to somehow guess what the right answer should be, and then plug it in and prove by induction, right? So guess and prove by induction. Okay. This would be a particularly challenging one to prove by induction, but we could try. So how would we guess an answer to this question? So I guess the real question is, how do you guess? The way you guess is by kind of squinting it. You squint it and say, okay, it kind of looks like this other thing. I know I'm not supposed to do that, I'm not supposed to use it. But just use it and see. Just to get a guess, I'm not trying to promise anything, right? The proof is going to be by induction. But for a guess, all bets are off. And then you can apply the Morse theorem, right? So suppose I gave you a Morse theorem reference that looked like this. Can you solve this? I mean, you should. I just give you tell you what to do, right? How would you solve this reference? Okay, this is the kind of question you could get at the final. I should say I haven't set the final yet, so you're not going to get any clues from today as to what's going to be the final. But this is the kind of question that could show up at the final. And within 5 minutes, you may need to know the answer to this question, unless you want to spend the entire 40 minutes just figuring this out. So what's the answer? Huh? And how do you conclude that?
Comparing it to the Morse theorem.
Okay, so let's draw the Morse theorem. So which case applies?
The third one.
The third one, because this is equal to that, right? Okay, good. So then log n. Now we know we're not supposed to apply the Morse theorem here because the a is root is not constant. Maybe we could, right? Let's guess n log n. So let's try to guess n log n and see what we get. So let's claim Okay? So let's plug it in. So we're going to prove this by induction. So we're assuming it's true for all values up to some number n minus 1, say. And so now we have t of n is equal to square root of n, t of square root of n plus n. By induction, since square root of n is much less than n, we can apply the induction hypothesis. So this will be less than equal to square root of n, c n log n, right? Plus n. Did I get that right? Yeah? Oh, it doesn't make, oh no, I got it wrong. C of square root n log square root n log n plus n, right? Yes? Which is equal to n times c times log of n divided by 2 plus n. Yes? Okay. Which is equal to Cn log n times half plus n over c log n. Did I get that right? No, that's wrong. Is that correct? Yeah? Notice that inside the parenthesis, the second term goes to 0 as n gets large. The first term is half. So I can say that this in the limit is less than equal to c times n times log n. Right? But that was the induction claim we wanted to prove. So we're done. So we have now shown that t of n is less than equal to c of n log n. Are we done? Can we stop here? There's a thing about guess and check, right? If you guessed it and you checked it and it worked, you're happy. But what don't you know? What can you not be sure about? So in other words, maybe it's too loose, it's too pessimistic a bound. Maybe t of n could have been a lot better. Well, you know, if it can't be n log n, it must be n. So let's try n, right? So let's try n and see. So the next thing we're going to try is t of n claim is less than equal to c times n. And again, you will assume by induction this is true for small values, and we'll prove it for n. So again, t of n is less than equal to square root n, t of square root n plus n, equal to, which is less than equal to square root of n, c times square root of n plus n. Is that correct? Yeah? Which is equal to c of n, c times n plus n, which is equal to c plus 1 times n. This is not good. We've just shown that if you assume that it's true for small values of n, it may or may not be true for larger values of n. I've got a c plus 1. There's no easy way to get rid of this. So my guess for n was wrong. I could not complete the induction claim. There's no way to manage this so that the c plus 1 becomes a c. There's nothing I can do now. There's no trick here. This is what it is. This was straight calculation. I didn't do any simplification here. I just plugged that in. So this doesn't work. So we know now that t of n is less than n log n, but it's more than n. And with guess and check, you're kind of stuck now. You just need better guesses. It turns out now, if you apply some insight into the problem, we said because of the master theorem, this thing is n log n, right? And if you think of why the master theorem says it's n log n, it's because you're basically going down to log n levels in your recurrence. Every time you divide into b pieces, right? And you b more pieces. If you keep dividing to b pieces, roughly log n base b. At that many steps, you go down, right? So one thing I was very careless about with the master theorem was that when things are like a is a constant, I don't really care about the base of the log. But here I should be a bit more careful about the base of the log because That doesn't really help us here, right? Okay. But because you're doing this, you're finding out at a level of square root n, the depth of your tree is going to be a lot less than what it would normally would be. Okay? In fact, the depth of your tree, if you divide by square root n at every step, is going to be log n. And to solve that, I'm basically claiming that if the d of n is the depth of your tree, I'm saying d of n is equal to d of square root n plus 1, because every time you factor by 1, you lose that. The solution for this recurrence is d of n is equal to log n. And this you can do by unrolling, by the way. This you can just unroll and see what doesn't happen. But what that means, roughly, is that your tree depth is only log n, and you're doing n amount of work at every step because you have square root n fan out, you're doing square root n of them. So effectively your guess, the right guess should have been n log n. And if you plug that in, it will work. But with the guess and check, you can't always be sure. So the guess and check is a good way to get some bounds, but you may not get a tight bound unless you can apply some other instinct. But it's a good way to get an initial bound, to get a sense of where it's going to go. Okay? So just again to review, to solve recurrences, you have basically 3 tactics. You can do unrolling explicitly. You can use the Moss theorem, which hopefully works for many cases. Or you can just guess. And to guess, it doesn't matter where your guess comes from. Literally just close right, dribble that would be a guess. As long as you can prove it. And that's the point I want to make here, that the proof of the guess is by induction. And that's it. Okay, any questions so far about this? So, hopefully going back to your memory and remembering those 3 tricks. Okay, so if there are no questions, I'm going to move on. Okay. So they said recurrent solutions comes up whenever you have a recursive algorithm. And the most basic kind of a recursive algorithm design is divide and conquer. Okay. So in divide and conquer, you have some input, you divide into a bunch of pieces, and you recurse on each piece. And then you combine them up in something. And the recurrent solution comes from how you divide and how you combine. So we've talked about running time. We said, okay, this is how you prove that you get a certain running time, and that's what you apply here. How do you prove these algorithms are correct? What do you do to prove correctness for divide and conquer? Sorry? Induction. And again, you need to use induction because you're recursive. Induction is a recursive proof. But induction proof makes sense here because you're saying, look, assuming that my recursive pieces worked, induction, the whole thing should work. This is how we design a divide and conquer strategy. You divide into pieces, assume the pieces solve the problem correctly, and assuming that, try to figure out how to put them back together. So divide and conquer proof of correctness is induction, where all the work in the induction is showing the merge step works. Right? So every divide and conquer algorithm has 2 parts, right? Step 1 is divide. Step 2 is conquer. This you get from induction. The correctness of this step comes from induction. The correctness of this step is actual proof. So whether it's merge sort or any other thing we looked at, right? Merge sort, we said, okay, we will prove that if we take 2 sorted sequences, induction, and put them together, we get a sorted sequence. And that's what we call it. Alright, so divide and conquer strategy, the design is recursive, the proof of correctness is by induction, the proof of running time is by one of those methods, which also in some sense is by induction. So if you believe that the problem you're being asked to solve has a divide and conquer solution, that is how you're going to prove correctness. And yes, you are going to prove correctness. Unless I explicitly tell you otherwise, you'll be proving correctness at any time. There's there's a reasonable chance, I won't say a high chance, but a reasonable chance that I won't expect you to write full proofs in the class exam. That takes time. But it's not a probability of 1 thing that it won't be off. But I also understand the long things. Okay? Any questions about divide and conquer? And how you think about how to write down a proof? So again, remember, algorithm, so in all of these things, right? Step 1, write down the algorithm. Step 2, proof of correctness. Do not go to running time proofs till you make sure it's correct. Number 3, running time. And for the algorithm, again, some element of pseudocode is fine. As long as it's well defined, then I can, if I can't trace out what you're supposed to be doing, it's not algorithm. I can consider myself a reasonable technician. that I can follow instructions with you. Okay. So you move on? Yes.
For the previous part where you explained the recurrence thing, are there some cases where manually creating a recursion tree and finding the depth of the tree would be helpful than all these?
Well, that's what unrolling is doing. Yeah. So the unrolling, I gave examples of unrolling that's a line. Often it's a tree. Right, so in the squared end case, basically what you would say is, you'd say, okay, I have this, I have squared end pieces, and there are squared end of them, and I have squared end pieces, and there's squared end of them, or end to the 1/4. So you quickly realize the first level is squared end, the second level is end to the 1/4, the second level is end to the 1/8, right? And the ith level is n over 1 over 2 to the I. When that has to go to something small, which means I has to go to log n, right? Well, sorry, n to the 1 over log n is basically a constant. So you need 1 over 2 to the I, you need 2 to the I to be log n, which means I need to be log n. That's how you can tell the depth is 1. So yes, unwrapping the entire recursion tree is a more expanded version of unrolling. That's why this Fibonacci becomes hard, because there's so many different ways you can unroll it. There is a whole class of techniques for things like Fibonacci or T of n is equal to T n minus 1 that don't require unrolling. But that's something I didn't cover in class, so I'm not going to. But there is a whole, basically it involves thinking of this like a discrete differential equation and solving it that way. That's okay. And again, the other thing I didn't mention with recurrence is the things like floors and ceilings. Right? We've talked about how you might deal with it. I'm not going to give you a lot of grief over those kind of things. Right? For the most part, if you want to assume n is a power of 2 and not whatever floors, that's okay. Right? Because in some sense, as we saw, right, if we just prove it for powers of 2, then infinitely any number can be sandwiched between them, and it's sort of okay. All right. Any questions about divided conquer strategies and what you might have to do to design and prove this in algorithm actually works? Okay. So moving on. So what we said was that dividing conquer was kind of an easy form of recursion. And then we get to dynamic programming, where you did think recursively, but you didn't implement recursively. Which means that your analysis strategies or your design strategies work slightly differently. Unlike before, where you just designed it and did proof of correctness and running time all the same way, here you do something different. Right? You might think recursively, design it recursively, but that's not going to be enough, because a naive recursive algorithm will be very expensive. So there's no general broad guideline for dynamic programs, but basically the idea of the dynamic program, as we saw, was that you think that you can divide things recursively. It's not clear how to split. In that dividing conquer, you just split so things are on equal sides. In dynamic programming, it's a bit more clever how you split. You may need to search over all possible splits, and so you don't want to do that. But recursively, if you imagine there's a split and you can solve it, then you get the answer. But the trick is to observe that when you do this recursion, you are repeating subqueries many times. And of course, Fibonacci is the easiest example of this, where there are only n different answers, but you keep hitting them over and over and over again. N minus 1, N minus 2, N minus 3, keeping the same things over again as you do your recursion. And so you have to, so the dynamic programming design process is sort of think recursively, find repeated subproblems, record them the first time, and then sequence the computation of the subproblems. So this is not the algorithm, this is just the way you think about it. But this step is the bottom-up part. And this is the top-down part. So we think top-down, implement bottom-up. And we've seen a number of examples of this. I'm not going to go through examples right now. But again, especially when you're dealing with things in a matrix or things in an array, it seems like you have to do a lot of work to find the right split, but really only so many different splits. So you just essentially guess the right split. And guessing basically means try them all, or try the best one you want. And that's the other part of dynamic programming. If you're trying to find the best answer to a problem, you can show that the best answer comes from the best answer to some previous subproblem. So if you can produce the best out of that, you can produce the best out of this. So direct drawing proofs of correctness are usually by induction. The proof of correctness is again by induction because you can use the recursive formulation. You don't care it's expensive, you can use the recursive formulation. And then the proof of running time is basically by the bottom-up analysis. You look at how you actually end up implementing it. Anything like that. So it's a little trickier, right? It's not as simple as a dividing conquer, but you get a bit more power. Any questions about dynamic programming in general or about the things that are important here?
How was it that we proved that the optimal substructure probably holds for something?
Yes, so in a dynamic programming problem, when the goal is to find the best something, the optimal substructure property says that the best answer for the problem can be expressed in terms of the best answer for some subproblem.
Yeah, and we proved that by
Induction. Whenever you have subproblems, things of smaller size, you should think, okay, this problem needs an induction. It's usually used. Because you can rely on the fact that the subproblem is in fact optimal. And then say, okay, can I now argue this? Because it's not always clear. I mean, there are problems for which the whole problem itself needs to be solved. If you break it up in any way, you lose the entire information about what the optimality is. And these are typically very, very hard problems. They're hard because you can't look at small pieces and infer something. Problems that admit the dynamic problem solution are somewhat easier because saying, look, I can look at small pieces if I break them up carefully and then put them together to find a bigger answer. Divide and conquer is even easy. Like break it up any way you want, it's still going to be fine. Dynamic programming, you can't break it up any way you want, but if you break it up carefully, you can still do that. So it's a little bit more complicated. Okay. And of course, next comes our good friend, greedy algorithms. So again, greedy algorithms are often the first way you might think of trying to solve a problem, and that's fine. But they're often not the last way, because they're always the best. The thing that makes a greedy algorithm, hard is trying to determine whether it's actually optimal. That's the hard part. For many of the other problems, proof of correctness by induction. Done. It's recursive, you're done. The greedy algorithm, that's actually not that clear. You can't prove, well, you can think about induction as helping you, but the proof is a bit more tricky because you have to reason, not just, you're trying to optimize something. And so you're not reasoning about what the algorithm does, you're saying, well, how do they do compared to the best answer possible? And so with the arguments we've seen in class basically involve saying, you know, one of two things, right? One is you look at what the greedy algorithm is doing, you look at what the optimal solution might have been doing, which might be different from greedy in some way. Look at the first point in which they differ. And you say, look, you know, at the first point in which they differ, the greedy algorithm is still doing better. And if I take one more step, I'm still going to do better. So by the end of the process, I'm at least as good as optimal, but I can't be better, so I must be optimal. That's one way to argue it. The other way to argue is kind of the mutation argument. Right? Say, look, you're optimal, I'm greedy, right? I'm going to change you to look like me. In one step, there's a place where we first disagree. I'll just change you to look like me. Now we disagree one bit less, but your cost has not improved. And so if you keep doing that by induction, we get to a point where we are identical and your cost has not improved. Therefore, my cost must be good. Okay? So this technique, right, is basically a sort of an editing technique where you imagine an optimal solution. You don't know anything about it except that it's optimal, and it somewhere differs from you. If it didn't, then I can argue. Then look at the first point of difference and say, look, I was very aggressive, you weren't. If I change, you know, your choice to my choice, it will not hurt you because of the nature of the problem. That's why you have to be clever with the problem and say, look, this choice won't hurt you. And now we are one step closer to being identical and the cost has not changed. So this is not any, you know, this depends a lot from problem to problem. But that's the basic principle, right? So basic proof idea.
You can't see.
Sorry? You can't see. That is true. You cannot see. Now you can. But it's going to sleep. So the proof idea is slowly change ought to look like reading without improving. So it might stay the same, but there is more strictly. And why am I changing ought to look like greedy? Why can't I change greedy to look like ought? Sorry?
Because we don't know how.
We don't know what ought looks like. If I'm going to change myself to look like, I don't know how to change it. It could be anything. But I can change ought to look like greedy. You know, like the mountain won't come to me, I can go to the mountain. Ultimately, the goal is to make us look the same. It doesn't matter how you do it. But do it without changing cost. That's the key, right? You have to show that you can do this without improving without decreasing costs. You're changing optimal. Optimal is obviously the best one. If you can improve, you're actually very happy. That's the most important thing. It's one thing to say I'll change, but if you don't prove that it's not worsening, then you could be getting a lot worse, and I'm not proving anything. And if you can't do this, so remember the design process really should be, let me try to break it. Always be trying to break it first. It's a lot easier to break one of these greedy algorithms than it is to prove they're correct. So don't waste your time trying to prove it correct if you can find a good break. If you don't have a good break, I might tell you, okay, this strategy for greedy is bad, I may need a different strategy. But do try to break it. That should be your first instinct for the greedy strategy, not to try to prove this. Okay. So here as well. Always try to find counterexamples. And if you struggle long enough without a counterexample, then you should be trying to reason this. But the inability to find a counterexample is not a proof of correctness. Remember that. The only thing that's a proof of correctness is the actual proof. If you tried very hard and you find a counterexample, that does not mean it's true. Question? And related to greedy algorithms, we also talked about local search, right? Where make small improvements from some starting answer. So local search procedure says, look, I have one answer. Maybe it's good, maybe it's bad, I don't know. I'm going to only allow myself to make small changes. So take these two edges and swap them if the matching cost gets better. But only two, don't take more. And then do that for a while until I can't make any improvement. So now that I'm stuck, I can't make any improvement, I'm kind of in a local min. And then sometimes you want to argue that this local min is optimal, or you want to argue this local min is good enough. Right? So we saw we can get a two approximation, and if you do more things, if you reached out further to look at your perturbation, you can get a slightly better approximation. And again, there the proof basically will say something like, you know, I have assumed that I have made all the local changes I can make. And assuming that I've made all the local changes I can make, I can't get any better using local changes. Therefore, and the proof will generally go if the optimal solution is very, very far away from me, then there must have been a local change I could have made. That's roughly how these proofs work. Again, they're not that simple. They depend on the problem, so I can't give you a general rubric to prove them. But you have to use the fact that you made all the local changes you can make as part of your reasoning. If you're not using that in your proof, then you're not really proving it. That's critical. It's like, okay, I cleared out all the area around me. There's nothing that's good in this area. I've checked. Anything that's good has to be much further away. But then I should have been able to get a little bit closer to it. All right. What do we talk about next? After we develop this, what is our next topic? Right? Guts and flows. We talked about flows next. And what was weird about that topic was that even the assignment, we spent a lot of time talking about how to do max flow, to make cut. But then when I gave the assignment, I asked you to design max flow and algorithm. I asked you to do something very different. What did I ask you to do? I asked you to take an arbitrary problem and map it to a flow for that problem. And later on, now that we looked at linear programs, you can see why I asked you that, because those are special cases of linear programming, and really what you're doing is write a linear programming formulation and so on. But a nice one where you can really see what's going on. And this is not to say that there isn't interesting work to be done to study how people design flow and canal. There is. But for the purpose of this class and the kind of use most of you will have for algorithms in your future work, some of you, few of you might actually want to do algorithms for research work, but most of you are doing something else. In that case, the way I talk to you about flows and cuts as a way of modeling a problem is probably the more useful way, tool you're going to have at your disposal. And so how do we talk about, so if you want to take a problem and solve it using flows, what do we have? What are the steps? Maybe a refresher in your memory. What do you do? So you have a problem, and I tell you, oh, I should be able to solve it using flows and cuts or something. What do you do?
Should I take the first?
Go ahead.
Consider the vertices and the vertices flow, maximum flow. Consider the vertices, what would represent the vertices in the graph, and then what would be the maximum flow of each step?
Well, what will be vertices? What will be edges?
Yes.
What will be capacities? What will be a source? What will be a sink? And then think about what flow would look like. Remember how for linear programming I said, okay, you need to figure out what the variables are, what the constraints are, and what the objective is? That's kind of what you're doing here too. What are the vertices and edges? The variables. Right? The constraints are given to you because you have flow constraints. So you don't think of the constraints, they're just baked into your problem. And then the objective is how you maximize, right? So figure out what are your vertices. So in other words, what you're doing is you're taking the problem, some problem, you have an instance of a problem, and you map it to vertices, edges, capacities, and a source, and a sink. And once you've mapped that for that particular problem, what do you do next? What do you have to show? Two things.
Yes. So, as in one is if we have the solution to the flow problem, then the corresponding problem can be solved.
Yes.
And vice versa.
And vice versa. So you have to show both things, right? So typically you're saying this problem needs to be solved. I need to produce some widget that maximizes something or the other. In your flow problem, okay, I have to compute a flow that has some property. Maybe it's a max flow, maybe it's a min-cost flow, maybe it's a circulation, maybe it's a whatever it is. Maybe it's a feasible flow because you have demands and all. You have some property there. And the question is, if you can compute an answer here, can you reconstruct a solution here that's valid? If you had a solution here to begin with, can you map it into the flow problem and get the solution that is prescribed? So it's not just mapping the solution, it's also mapping the solution with the properties desirable for a solution here, right? If a solution here says the max flow should be at least 5, and I have a solution here, when I map it there, the solution should be at least 5, because that's what I'm looking for. Correspondingly, if I get a solution here, size 5, and I put it back here, it should be a valid solution to this problem. Whatever the criteria was here, optimum solution to this problem, whatever. Okay? So in any flow setting, you have these 3 things you have to do. You have to describe how you map an instance of the problem to vertices, edges, capacity, source, and sink. You should do that first. Then you should say, what is the problem specification? In other words, what is a successful outcome there? What's a successful outcome here, which is given to you from the problem? And then you prove your 2 things. So successful outcome, so I'll just put these 2 arrows here. Say that a successful outcome on the left is a successful outcome on the right, and a successful outcome on the right is a successful outcome on the right. All these 3 things need to be there. And once you do that, you're done. Just like how the linear program is, okay, do the whole thing, solve the linear program somehow. Here also, run the max flow somehow. And then just look at the answers. It's the same design pattern. Okay.
Is it correct to say that any problem which can be reduced to the flow problem will always have its optimal solution as integer in the linear program? Because you can only get the integer solution.
If it turns out that you're using integer coefficients or rational coefficients. And maybe you map it to your flow problem, maybe you put square root of zero. Okay. Then not here. Or you put some rational numbers, that's not an issue. So, depends. If you can map it to a instance of flow with integer values, then sure.
I'm sorry, I didn't understand.
You understand the question or yes?
The answer.
So you understand the question.
Yeah.
So the question was, can you always assume that if you map a problem to flow, that an integral solution will give an actual integral solution? And my answer was, well, it depends on how you do the mapping. If the mapping involved capacities that were irrational numbers, then that's no longer true. Maybe it needed that. Maybe if the capacities were rational numbers, then it's no longer a guarantee. With rationals, maybe you can normalize everything, but then your numbers get too big, and there's a whole bunch of other things. So it depends. Other questions? So hopefully this has been a helpful refresher, a reminder of what we covered and what you need to know to give a correct answer to a question. Right? So I'm not reviewing the class as in, okay, here's what we taught. It's more like very focused on, okay, if I have to ask you a question, you need to give me an answer, you get points for it. This is what things you need to worry about. We'll do something similar on Monday with randomization and linear programming approximation as well. Again, there'll be maybe a little refresher on what's expectation. Go and read some of these stuff again, because you'll need to remember some of these things. You'll need to have those Instagrams. Okay? Alright. I will see you on Monday, and I will make the note about the cheat sheet today in the answer. So you can prepare one, 8.5 by 11 sheet.